You know, it's pretty wild to think that sometimes an entire revolution can be traced back to a single moment. For modern AI, that moment was the publication of just one research paper, way back in 2012. Today, we're going to break down the paper that taught computers how to see and, in doing so, basically change the world. So let's dive in. For decades, this was one of the absolute biggest challenges in computer science. I mean, how do you teach a machine to look at a picture of a cat and know it's a cat, and not a dog or a car or just a bunch of random pixels? That's the huge question we're tackling today. Okay, so to really get how big this breakthrough was, we need to understand the mountain researchers were trying to climb. Because back in the early 2010s, the whole field of computer vision was, to put it mildly, kind of stuck. Just think about it for a second. A cat can be in any pose, right? In any kind of lighting. Maybe it's partially hidden behind a couch. It could be any breed, any color. For a computer, that's practically infinite variation. And as the paper's authors pointed out, the old data sets were just too small. We're talking tens of thousands of images, which just wasn't enough to capture the beautiful chaos of the real world. So to solve this, researchers needed a much bigger sandbox to play in. And that's where ImageNet came in. This wasn't just a slightly bigger data set. It was astronomically bigger. We're talking over 15 million high-res images, all meticulously labeled across more than 22,000 categories. This was the raw fuel that the next generation of AI was going to need. And to really kick things into high gear, the ImageNet Challenge was born. You can think of it as the Olympics of computer vision. Every year, teams from all over the world would show up and unleash their best, most clever algorithms on the ImageNet data. The goal was simple: get the lowest error rate. It was the ultimate test. Then came 2012. A small team from the University of Toronto submitted a model that was, well, it was unlike anything the competition had ever seen before. It was big, it was deep, and frankly, it was about to change everything. So the model they built was a specific type of neural network called a convolutional neural network, or a CNN. Now, the key idea here is that CNNs are specifically built with images in mind. They're designed to recognize patterns, like edges, and textures, and shapes, layer by layer, which is actually a lot like how our own brains process what we see. And the network they built, which we now know as AlexNet, was an absolute behemoth for its time. I mean, the paper just lays out the specs. 8 layers deep, 650,000 digital neurons making decisions, and a mind-boggling 60 million parameters. You can think of these as tiny little dials the network can tune to learn from all that data. This wasn't just a small step up. It was like building a skyscraper in a field of bungalows. But here's the thing, it wasn't just about size. The team, led by Alex Krzyzewski, Ilya Sutskever, and the legendary Jeff Hinton, baked in some incredibly clever and totally crucial innovations that made this massive network actually, work. First up, something called ReLUs, or rectified linear units. Before this, most networks used functions that were pretty slow and would often just kind of flatline during training. They'd stop learning. But ReLU was so simple and so much more efficient. Basically, if a signal is negative, you just ignore it. If it's positive, you pass it along. That's it. And this simple switch made a huge difference. And here's why it mattered so much. This chart, which is based on one from the paper, shows that networks using these ReLUs could learn up to 6 times faster. Without that massive speed up, training a network this big would have been, well, pretty much impossible. Next up was a hardware problem. Their model was just so enormous that it literally couldn't fit into the memory of a single graphics card, or GPU, which was the best hardware at the time. So, what'd they do? They came up with this really clever solution. They split the network in half across 2 GPUs and programmed them to talk to each other. This was a real feat of engineering, and it was totally essential for handling a model of this scale. And finally, they had to stop the network from just memorizing the training images instead of actually learning the general concepts. It's a classic problem called overfitting. They used 2 main tricks here. First was data augmentation, and second, this brilliant technique called dropout. Okay, imagine you're training a basketball team, but for every single practice, you make a random half of the players sit on the bench. The players left on the court are forced to get better, and they can't just rely on the same star player every time. That's what dropout does for neurons. It forces the network to learn more robust ways to solve the problem. So, they had the massive data set, the huge network, and all these secret ingredients. The stage was set for the 2012 ImageNet Challenge. The big question was all this work actually going to pay off? Oh, it didn't just pay off, it was a demolition. The top 5 error rate basically means the percentage of time the right answer wasn't in the model's top 5 guesses. The runner-up that year had an error rate of 26.2%, which was pretty respectable, but AlexNet came in with an error rate of just 15.3%. This wasn't just winning, this was a whole new ballgame. Just look at this table from the paper. That gap between first and second place was over 10 percentage points. A leap that big in this field, well, it was basically unheard of. Overnight, everyone in AI knew that something fundamental had just changed. And the impact of this one victory went so far beyond a single competition. This was the moment deep learning went from being this promising, kind of niche academic idea to being the undisputed future of artificial intelligence. And this is what that performance actually looked like. These are examples right from the paper. The network nails the leopard, no problem. It gets the container ship. And look at this. It even correctly identifies that tiny little mite in the top left corner. It could see objects in context, which was a massive step forward. But maybe even more profound was that it learned abstract concepts. This slide shows images that the network thought were similar based on its own internal logic. Look at how it groups different breeds of dogs together, even in different poses. It wasn't just matching pixels anymore. It was starting to learn the very essence of what makes a dog a dog. And, the authors really summed it up perfectly themselves in the paper's conclusion. They wrote, "Our results show that a large, deep convolutional neural network is capable of achieving record-breaking results. So the depth really is important for achieving our results." This single result created the playbook for modern AI. The formula it established, taking massive datasets, throwing massive compute power at them with GPUs, and adding a few clever tricks like relus and dropout, that is now the foundation for almost every major AI system in the world, from the camera in your phone to self-driving cars. It all started right here, with one landmark paper that proved deep learning wasn't just hype. It taught a computer how to see, and in doing so, it opened all of our eyes to a future powered by artificial intelligence. The only question is, what comes next?